Hello everybody! In today's video lecture, you are going to learn about center of mass. Please don't forget to take notes as you watch the video. Motion of a system can be described in terms of a special point on a system called center of mass. The system could be a collection of atoms in a container or a solid extended object like a gymnast. Up until this point, we worked with small point objects such as a small rock or a ball. It is easier to predict its motion when thrown up in the air. But what if we had an irregularly shaped extended object such as a wrench? Imagine holding a wrench from one end and throwing up in the air. Can you visualize its motion easily? Or take a look at this wrench that is sliding across a frictionless table. It seemed to be turning and wobbling all around the place. But if you take a look at these white dots, what do you notice? I see that these dots are moving in a straight line path with equal distances. What do you think this white dot represents here? You guessed it right. That's the center of mass of the object, and it is moving in a constant speed in a straight line direction. Therefore, if you can locate the center of mass of an object, you can predict its motion with greater ease. It is as if the object or the mechanical system moves as if all its mass were concentrated at the center of mass. Well, that's interesting. Even more interesting than that, internal forces during collisions or explosions won't change the projectile's center of mass. The motion of the center of mass will continue as if nothing has happened. As you see on this illustration, a projectile is split into two, and if you know the original path and if you know the location of one of the fragments, using this information you can easily figure out the location of the second fragment. Center of mass is often called center of gravity, which is the average position of all the particles of mass that make up an object. Center of gravity or center of mass could be used interchangeably, except if we are dealing with a very large object and a very tall object such as a skyscraper. In that case, center of mass could be in the geometrical center of the skyscraper, and center of gravity could be slightly lower because the mass from the lower, closer to the earth side, is going to be pulled to the earth with slightly greater force than the mass from the top of the skyscraper. Now, just like we discussed earlier, we don't need to have a single object to talk about the center of mass. We can have a system such as a solar system. If all the planets were lined up on one side of the sun, the center of gravity of the solar system would actually lie outside of the sun. Now, if an observer, like an alien observer, viewing our solar system from far, far away, only the sun would be visible to them because it creates its own light, and then the other planets will not be visible. But then, if the observer views the path of the sun, he or she may get confused because the motion of the sun is going to look a little weird, just like the motion of the wrench. So it turns out the sun and the planetary system can be considered like a wrench with the center of mass right here. So an observer would see the sun, which would be the heavier portion of the wrench in this case, like this, as the sun moves in its path. So instead of moving a straight line, sun will appear to be wobbling up and down to the observer like that. Well, actually, this is how many of the planetary systems were discovered by astronomers by the wobble of the stars. Now let's see how can we locate the center of mass. The center of mass of any symmetrical object lies on its axis of symmetry, such as these objects here. And it is easy to balance an object on its center of mass. Supporting the center of mass supports the whole object. Now, what if the object you are trying to locate the center of mass is not uniform? Then we can use the fact that if you suspend any object at a single point, the center of mass of the object will hang directly below of the point of suspension. So to locate the center of mass, you can construct a line beneath the point of suspension, and the center of mass lies somewhere along that line. For example, you can suspend this map along this point as seen, and then you can construct a line on the point of suspension. So you know that the center of mass must be at somewhere along this line. So when you just hang the map from this location next, then you are going to have another line, and where the line intersects is going to be your center of mass. It turns out the center of mass of an object may be located where no actual mass exists, such as these examples right here. Or if you had a donut-shaped object like this, where would the center of mass be? It would be exactly in the middle, where there is no material. Now, let's talk about the mathematical model for locating the center of mass, which is average location of all particles of mass. The x-coordinate of the center of mass can be found by adding the horizontal distances multiplied with the masses of each mass in the system divided by the total of all the masses. Similarly, if there is a y-coordinate, it can be found, y-coordinate of the center of mass can be found as the total of y distances multiplied with the mass of the object. I is the count here, like if there are 3 objects, then you need to do y distance 1 times m1 divide plus y distance for the second object times m2 plus y distance for the third object times m3 divided by the sum of all the masses. Now let's see it in an example. We have 3 objects here and we need to find the center of mass of the entire system. Well, the coordinate axis is not given, so we don't know where to start our measuring or where to reference everything. So it is easy though, you can come up with your own reference frame. So I'm going to take the coordinate axis right here, so the origin is going to be the middle of my 2 kilogram object right there. I think it is pretty convenient. Now let's find the x-coordinate of the center of mass here. So let's call this one object 1, object 2, and object 3 right there. Now the horizontal distance of object 1 is to the origin is 0, and 2 is also 0. The horizontal distance to object 3 is 3 meters, so I'm going to go 3 times the mass, which is 1. And the sum of all the masses, 3 plus 2 plus 1. So I'm going to end up with 3 over 6, which is half a meter. This means the center of mass lies somewhere half a meter to the right of my origin. So let's do the same for the vertical. So object 1 has a vertical distance of 4 meters to the origin. So 4 times its mass 3, and the object 2 is at the origin already, and object 3 has no vertical distance to it, so it is 0. And divide this with the total masses is going to be 6 again. So this is going to be 12 divided by 6, and it is 2 meters. This means the center of mass for this system is going to be half a meter to the right and 2 meters higher. So I'm guessing half a meter is going to be around here, and 2 meters is going to be here. So this should be where the center of mass must be located for these three objects. If there are no outside forces, total momentum of the system remains constant. So is the velocity of the center of mass. In that case, we can calculate the velocity of the center of mass by finding the total momentum of each object divided by the total mass of the system. Here's an example. In this case, two pucks are sliding at the same direction, and they have different velocities and masses. So all we have to do is find the momentum of each puck and add them together. So our equation becomes m1v1 plus m2v2 divided by the sum of all the mass. Plugging in, we can find that the center of mass is going to have a speed of 11 meters per second. Here is a different concept, area of support. The shaded area bounded by the bottom of the chair legs defines the support base of the chair. Similarly, you have a support base, which is the entire shaded area. If you think about it, if you extend your stance, you are going to have a bigger area of support, which will help you balance yourself easier. Let's see why. Condition for stability or balancing an object is if the center of mass of an object is above the area of support, the object will remain upright. If center of mass extends outside the area of support, the object will topple, just like what you see over here. So these rocks miraculously stay upright, or their center of mass must be somewhere along this line, because this is the common area of support for all of them. And these objects will be stable as long as the center of mass is supported. Equilibrium is said to be unstable when any motion will lower the center of mass of the object. Equilibrium is stable when work must be done to raise the center of gravity. As you see here, when you try to tilt the cone, you have to lift its center of mass. And equilibrium is said to be neutral when the displacement would neither raises nor lowers the center of mass. Lower the center of mass, more stable the object gets. As you see, in both positions, this rectangular object is in stable equilibrium. When you try to tilt it, you have to lift the center of mass. In the first case, you have to lift the center of mass slightly, so you need to do a little work before you can tip it over. But on the second case, you have to lift the center of mass a great big distance so that you can tilt it. This means the second object on its side is more stable, and it takes a lot of work to tilt it over. A pencil balanced on a hand like this is in unstable equilibrium, because any motion of the pencil is going to lower its center of mass. However, if you add some potatoes to the ends, the overall center of mass of the system is going to be located right here. When you try to tilt the pencil with the potatoes on, you actually need to raise the center of mass. This means this one is in stable equilibrium. Lowering the center of mass is very important for a high-rise building, such as the Space Needle in Seattle is so deeply rooted that its center of mass actually is underground. So it is impossible to tip the Space Needle intact. It would rather break because it needs any kind of motion will have to raise its center of mass. Objects tend to move or roll only if this motion will lower their center of mass. Consider a table tennis ball placed at the bottom of a container of dried beans, for example. When you shake the tray, what will happen? The ball will be nudged up to the top. Guess why? What's the reason? We are going to talk more about center of mass in class. Thank you for listening, and don't forget to take your quiz.